Hello, everybody. Welcome back to Learning as a Hobby. In this video, I'm going to be going over my summary of section 1.3 in the Simmons book, Differential Equations with Applications and Historical Notes. And this section is on families of curves and orthogonal trajectories. So you can see it's a relatively short section, but I'll go through my summary notes. And actually, I added a bit of a derivation that is not actually in the book. I'll get to that when we come to it in the notes. So let me bring up the my summary here. Okay, and as I usually always say, you should read through the section yourself because, again, this is just a summary. There's a lot more information in the section itself that I'm not going to touch on here. This is just a sort of like skeleton of the chapter. All right, so let's just jump into it. So the curves of any one parameter family are integral curves for some first order differential equation, and we could show that here. So if f x y c equals 0 is a one parameter family, if we differentiate that with respect to x, then we get this one parameter family of differential equations, right? And if you eliminate the parameter, then we get the associated ordinary differential equation that we have written here. Right, so that's the process for finding the ODE from a given one parameter family. Right. So, and then he just goes through a couple of examples here. So here we have the family of circles centered at the origin of radius square root c. Again, if you differentiate, just following that procedure, if you differentiate with respect to x, then you get this equation here, and you can divide everything out by 2 just to write it in a simpler form, and that looks like this. That's your differential equation. And if you want to solve for dy dx, you can actually do that here. That won't always be possible, but here we can. And we get that dy dx is negative x over y. That's the differential equation for that family of one parameter family of curves. Right, we can do the same thing for another family of curves. Here we're looking at x squared plus y squared equals 2cx. Again, these are circles, but they're not centered at the origin. They lie along the x-axis, so they will look something like this. They'll lie along the x-axis here, and they shift left or right depending on the value of c. Okay, so that if you differentiate that with respect to x, you get 2x plus 2y dy dx equals 2c. Don't forget the implicit differentiation, right? And then we have to eliminate the parameter, which we can do by solving this equation for c and then plugging that expression in for c over here, which gives you that on the right hand side. And then solving for dy dx gives us this differential equation. So this is the differential equation for this one parameter family of solution curves. All right, that's the idea. From there, we're going to look at orthogonal trajectories. So once you have a one parameter family of solutions, sometimes it's important to know about the family of orthogonal trajectories. Orthogonal meaning perpendicular. So everywhere that the curves intersect, they intersect at right angles. That's what orthogonal means. So the process for doing that is first you have to find the ODE. So, do a procedure, something like we had up here. Okay, and then if you remember from your Calc 1 course, the orthogonal the normal line, right? The line that's orthogonal to a curve at a given point has the negative reciprocal of the slope of the tangent line. So replace dy dx by negative dx dy to obtain the ODE for the orthogonal trajectories. And then you just solve the new differential equation, and that'll give you the one parameter family of orthogonal trajectories to the original one parameter family. So let's actually do an example. So going back to that differential equation for those circles that were centered at the origin with radius square root c. So here we get x plus y, dy dx equals 0. If we replace dy dx by negative dx dy, and then solve that equation for dy dx, we get this differential equation here. Whoops. Dy dx equals y over x. And if this is a separable differential equation. If we separate variables, we get the equation 1 over y, dy dx equals 1 over x. And then finding the antiderivatives, we get natural log of absolute value y equals natural log absolute value x plus c. And then, raising both sides to powers of base e, and simplifying, you get this one parameter family of curves, which is all lines that pass through the origin. And just I'll draw the picture just so you can see what the curves look like. So the circles that are centered at the origin, they look like this, right? And so on. There's an infinite number of them. The lines that pass through the origin with slope c look like this. Again, there's an infinite number of them. But notice that those lines are all normal to the tangent lines of the curve at that point, right? They're all perpendicular. So this is the orthogonal family of curves to the circles that are centered at the origin. Okay, sometimes it's more convenient to express the family of curves in terms of polar coordinates. That is true for the second example that we had over here. Here it's easier to represent this differential equation in terms of polar coordinates and then solve for the orthogonal trajectories using the polar representation. But there's something we have to talk about first. There's a derivation that we need. So here, if you remember, if you're converting from polar coordinates to Cartesian coordinates, these are the equations you have. Or if you like, you can think of x as this function of r and theta. So x is r cosine theta, y is r sine theta. And if you differentiate both of those equations with respect to theta, you get these expressions for dx d theta and dy d theta. And if you recall your single variable calculus, that means that, actually, let me do this on the whiteboard so that there's space to write. Share. So if you recall, dy dx is given by dy d theta over dx d theta, right? Which gives you, let's see, I have to rederive it now. Sorry, y is r, where's the pen? R sine theta, x is r cosine theta. So if you write down dy d theta on top, you end up with r cosine theta plus dr d theta sine theta. And on the bottom, you get negative r sine theta plus dr d theta cosine theta. So this is the expression for the slope of the tangent line with respect to the x-axis. So just drawing the picture here, let's say that this is your curve, this is the point, this is the tangent line, this is the angle phi that the tangent line makes with the x-axis. So that means that tangent of phi is dy dx, which is given by this complicated looking expression here, which is not, you probably remember this from single variable calculus, but it's not as convenient method of writing the slope of the tangent line as the method that we're going to derive here, which unfortunately is something that we didn't do when I took single variable calculus. But let me just show you real quick. The thing that you need is in Stewart's calculus, but unfortunately it's relegated and kind of buried in the exercises at the end of what chapter is this? And in the end of chapter 10.3, it's actually relegated to question number 77. It's almost the last question in that exercise set for section 10.3. It's this question here. So I'm going to derive the formula that we need, and I'll explain it as we go along in the derivation. He actually doesn't derive it in Simmons doesn't derive it. He has the picture here, but he just says this is what it is, and he doesn't really explain at all. So I thought that might be confusing. So and it might be. I thought it would be fun to derive the expression. So let's actually do that here. Just be aware that it's not done in the Simmons book. I wonder, I didn't look before I made this video, but I wonder if he makes you derive it in Spivak. I have a feeling that he probably does, knowing Spivak. But anyway, we'll do it here as well. So let me go to my notes because I derived the formula there. Okay, so instead of using that complicated formula for dy dx, what we'll do is we'll let phi, this is the Greek letter phi, let phi be the angle between the polar radius and the tangent to the curve, as opposed to the angle between the x-axis and the tangent line. So I have the picture drawn below here. All right, so this is the angle phi. This is the angle, oh, I'm sorry, this is not phi, this is the Greek letter psi. Sorry, psi. This is the Greek letters phi. Sorry, I'm getting my Greek mixed up. And this is the angle theta, theta, that the polar radius makes with the x-axis. All right, so just so we can see how everything is related here, tangent of theta is y over x. Tangent of phi is dy d theta divided by dx d theta. And tangent of phi is the slope, oops, sorry, this should be the tangent, should be to the tangent line, is the slope of the tangent line with respect to the polar radius as opposed to the x-axis. So if we just clear the picture here, here if I just redraw this triangle here, just so you can see what the angles are. These are alternate interior angles. I forget what they're called from geometry, but the angles here are the same, right? So you get phi over here. This is the angle theta. And this angle then here, if you remember, the three angles of a triangle add up to 180 degrees, or in radians, that's the same thing as pi. So you get this angle here. Whoops, this angle here is pi minus phi minus theta. And because this is a straight angle, meaning that it has measure 180 degrees, or pi, that means that pi is equal to pi minus psi minus theta plus phi. And solving for phi, you get that phi is theta plus psi, right? And this is going to be the key for deriving what we need. Which I do on the next page. All right, so tangent of phi is equal to tangent of, sorry, I keep saying phi, tangent of psi is equal to tangent of phi minus theta. And using the difference formula for tangent, that's equal to tangent phi minus tangent theta divided by 1 plus tangent phi times tangent theta. And then remember that tangent of phi is dy d theta over dx d theta. Tangent of theta is y over x. So we end up with this complex fraction when we plug everything in over here. And then just simplifying the complex fraction, we end up with this expression over here. And then if we replace x dy d theta, dx d theta, and y with the formulas that we derived up above, let me just remind you what those are. So this should have been psi here. So replacing everything, where did I write it? Oh, over here. Replacing everything with these formulas in terms of r and theta. We end up with this, which we can simplify. And when you do all the simplifications, you get a very nice simple expression for tangent of psi. So tangent of psi is equal to r d theta over dr, right? Which is a lot nicer than the formula that we had. Let me just remind you. Whoops, that's not what I wanted. That's a lot nicer than this complicated looking formula, which is the one that I believe they usually go over in like Calc 2 or whenever you did polar coordinates. So I don't know why. I mean, maybe they do go over that in other schools, but they didn't go over that in my class when I took calculus. So I just wanted to do that in my summary here in case people haven't seen that before. Let me go back to the notes now. All right, so you get this nice expression for the slope of the tangent line with respect to the polar radius as opposed to the x-axis, right? You get this nice simple formula. And then we can do an example using that. So to find the orthogonal family of curves to a family in their polar representation, replace dr over r d theta with negative r d theta over dr and solve the resulting ODE. So again, you just take the negative reciprocal, right? That gives you the orthogonal trajectory. So doing the example, let me just go back. That second example that we went over in the summary, where was it? This one here. So if you write that in its polar representation, we end up with this differential equation here. All right, and then again, just replacing this with the negative reciprocal, that gives you this differential equation, which we can solve because it's separable. So just take the indefinite integral, and you get that natural log of absolute r equals natural log sine theta plus an arbitrary constant. And here I'm writing the arbitrary constant as log 2c. The reason that I'm doing that, first of all, log 2c is just as arbitrary as a an arbitrary constant c, right? Because c can be anything, and the log is onto the real axis. The reason I'm doing that is because in the orthogonal trajectories, I want the constant to have the same value as where was it? As the constant here. So that for each pair of curves in the family of integral curves, I want the orthogonal trajectory to have the same constant, if that makes sense. Going back down, so if we solve the differential equation, we get that, and then take both sides of the equation as powers of base e and simplify, and you end up with this family of curves, and those are the orthogonal trajectories written in polar representation. If you want to turn it back into Cartesian representation, you can multiply this through by r, so you'll end up with r squared 2c r sine theta, and remember this is x squared plus y squared, and this is y, so you end up with the Cartesian equation for the the orthogonal trajectories, which are circles that lie along the y-axis as opposed to along the x-axis. All right, so those are the orthogonal trajectories using the polar representation. So that's essentially it. Like I said, it's kind of a short section, and there aren't that many exercises in that section, but I'll go through those in the next video. I haven't even had a chance to try them yet, but I'll go pick, like I usually do, I'll pick some interesting looking ones, and I'll do those in the next video. And then I got classical mechanics coming up next. All right, after the exercises for this section in Simmons. So let me stop the screen share. All right, guys, again, thanks for watching. Please like the video and subscribe if you like watching content like this. This way the channel can grow and YouTube can recommend the videos to other people that like this kind of thing as well. Until the next video, guys, keep learning. I hope you're enjoying the videos. I hope you're following along with them too, and that you're learning something. And I'll see you guys in the exercise video for Simmons section 1.3. See you guys then.